All right, you're all welcome once again to the second live class recap for the machine learning basic program. Last class, we looked at basic introduction to machine learning, and it's more like an introductory class. So today we'll be getting our hands a bit dirty, and we'll be doing some practical. So I mentioned earlier that these sessions are recap sessions. So if you want to benefit from, more detailed sessions, we have the past recordings for the bootcamp linked on the LMS as well on our YouTube channel. So do well to watch those recordings. Then would also link these recaps as well for like a backup and extra information. So we'll be navigating through using a case study. So today we'll be focusing on supervised learning with regression, and we'll be looking at some machine learning algorithms, how to build a model systematically from the start to finish. So that's what we'll be doing in today's recap session. All right. Okay, so I'm going to share my screen shortly. If you have your questions, you can just put them together, and when it's time for question and answer, we can ask them. Okay, I'm just going to get my screen up quickly. Just a minute, please. I believe you all can see my screen. So we'll be working on a very popular data set. It's called the Boston House Prizes. And like I mentioned during the last class, we talked about some basic introduction. What is machine learning? What are the type of machine learning problems that we have? And then what is classification? What is regression? And all of that. So under supervised learning, we have the regression problems and the classification problems. And like I mentioned during the last class, that the regression problems are when you're predicting a known label that is continuous. When you have a task ahead of you to predict a known label that is continuous. An example of a regression problem, we have the prices, we have humidity, we have temperature, we have any continuous column variable. When you're building a model that involves prediction of continuous functions, that is a regression problem. So assuming we have a problem at end, and this is a data set, Boston House Prizes. One of the ways to, get data set, I mentioned it during the last class. There are several ways you can get your data sets. You could be working in an organization, and then you have access to the database, or you could do your scraping of data online, or you could do questionnaires, surveys, what have you. However, this data set was gotten from Kaggle, one of the repositories. Kaggle is a data science platform where you can host competitions, as well as you have access to numerous data sets. Okay, so after downloading the data set from Kaggle, the first thing to do is to study the data set, how many rows, how many columns, and looking at trying to gain an understanding of what your data is like. I believe you can all see my screen. Yeah, okay. All right, so I haven't downloaded the data set. So if you can't, I think we have this data set on the LMS, but if not, if you go to Kaggle.com for people that want to work along, and you type Boston House Prizes, you see there's a very popular data set. All right, this is the HR. Let me search for Boston house prices. Okay, so we have a couple of notebooks that have been done using the Boston house price, but I'm actually looking for data sets. So let me click on this and see what it's like. Okay, so this was a competition. And then, okay, here is the link to the data set. I just, searched randomly. I could have gone through the data sets repository, but I just wanted to go through a faster means. And then here we have the data set. So we have other data set like it. We have the gender pay gap, California house prices, company bankruptcy predictions, Spanish wine quality data set. All right. Anyways, this is the data sets we're working on. So if you want to have it on your system, you can just download it. When you click on download, you can download it as a zip file and it goes to your local drive. I have it on my system, so I don't need to download it again. All right. So when you're working on when you're using Jupyter Notebook, ensure that your data set is the same location with your notebook, the notebook you're currently working on. All right. For people that went through the Python class, I think this shouldn't be new to you. So I'm going to be assuming everyone have a background in Python because of some things we'll be doing in the with this work. Okay, so we have this data description where we have about 14 columns and 506 rows from the data description. And we have the individual definition for what each column represents. So we have the crime per capital crime rates per town, portion of residential land zone for lots over 25,000 square feet, proportion of non-retail business, and all of that down to the median value of occupied homes in 1,000 in thousands of dollars. $1,000. So the next thing to do now, after going through the whole data description, we have that you need to know, okay, what do I want to do with this data set? Here, I want to predict the median value of occupied home. That is the price, the median price value. This is what we are predicting. Okay. From that's depending on your project objective. I want to make predictions of what is the median price value of occupied homes in this area in the US. Okay, given all of this feature, can I predict the median value of homes occupied? Why do you need to do that prediction? What's the motivation behind that work? It could be because maybe some people have issues with house purchases, and they need to know, can they have some sort of solution where they can just go to that solution, and giving them different by them imputing some parameters, they're able to see that, okay, this is the value of the house that would likely be in this region if I make investments in this place. So depending on what your objective is, but in this case, we want to predict the median value of owner-occupied homes in thousands of US dollars. All right, so the first thing to do now is want to do some data preparation and pre-processing. Okay. We have to import all the necessary libraries. For example, we'll be using pandas, which is for data manipulation. We'll be using it to read in our CSV file. So the Boston house price data set was in the CSV format when downloaded. So I have to use pandas for that. I might need NumPy for in case I need to recreate some columns in the data set. Matplotlib and Seaborn are visualization libraries. We didn't touch on that, but then you can learn it on this. It's not a difficult library to learn. And there we have the library documentation. Seaborn. If you type Seaborn, when you go through the notebook, it's easy to follow through once you have an understanding of Python. This is their documentation here. You can plot different graphs using Seaborn, and doing data analysis, you have to learn how to also do visualization, such as to interpret your results when you need to compare different features together. You have to understand what it means. So if you read this documentation, for example, it will give you like a background of you can just go to the tutorials and click on tutorial. It's going to give you a guide of different plots that you can learn. You can start with visualizing your statistical relationship, distribution of data, and all of that. It to give you like different backgrounds. I mean, different type of, like, this is what we'll be using. We're using the raw plots. You can specify what kind of, by default is a scatter plot function. So you can we'll be using this in our work. We have different type of plots. So if you go through this documentation, you see how it works and how to use it. All right, going back to our Boston data set. Boston data set. And the question, do you have a question? Your hand is raised.
I can't see the screen.
Okay. Can any other person see the screen? If you can see the screen, you can just react so that okay. I think maybe it could be your network. I think other people can see it. So I don't know. Could be the network. So you can check your network. All right.
Let me rejoin again and see.
All right, great. Okay. Okay, so moving forward, I was just showing you different libraries that you'll be using. So we're using Pandas, NumPy, Matplotlib, and Seaborn for visualization. And this, when you're importing your packages, you have to do import Pandas as PD. I believe we can do that. Matplotlib, import the name of the package. You are using the pyplots function from the Matplotlib package as PLT. Import Seaborn as SNS, and after the import, we are going to be using other libraries here, but basically I'm just taking it like step by step what you need to do. So the next step is to read in your data set. And while you're reading your data sets, you're reading it such so that you can have like an overview of what your data set looks like. So you're going to use your PD .reader underscore CSV, the name of the CSV file, the file name in brackets, and then use your .ed function to read it. Now, you can see that you'll have your data sets in a nicely put together format. You have the crime, you have the crime percentage, I believe, or crime ratio, or per capita crime rate. We have the proportion of residential landed zone for lots over 25,000 square feet, and all of that. Okay, the zone, the indians, and the most important column we are interested in is the median value. That is the price. And this is, I believe, this is in thousands of dollars. So 24,000. So this should be, yeah, 24,000 US dollars and all of that. Okay, then all of this are your features. And then this is your targets that you want to predict. Okay, so because this is a data set related to house pricing, you're having, and this is more like a dummy data set. Real life data sets are not as nicely put together like this. You might have like so data set might have like 100 columns. This you just have 14, and then it's very messy. Like you might have so many missing values and all of that. So I'll be showing you what missing values is. If you were in the Python class, you would, understand we talked about null values, and how to deal with them. Okay, so some data sets might have missing values. Some data sets might even have texts, like you have to convert all of your text columns. You have to do encoding, some sort of encoding, whether your label encoding or one-hot encoding. So we are not doing all of that here because everything is numeric, so we don't have so much work to do. But then we are still going to continue with our data preparation process. So having read in your data set, checked the edge, then the next thing is to also further investigate. Let's find out some more things about our data set. So you can use your .info function to check, give you information about the data sets, check it's not no you know that your data set's 14 columns, but then you're checking for null values. There are no null values, which is very good because null values are not so good as well. When you're building your machine learning model, you have to learn how to deal with that so that so that we have, we have a balance data. So when you're doing when you have data sets with null value, it affects the performance of your machine learning model. So we don't have null values here and we are good. So now next, what we need to do is to check for duplicates. Now, the reason for duplicates is that sometimes you might have some data sets and then like I was working on the project and I thought I had got a very nice data set. It was like almost 2000 columns, 2000 records. And then you can imagine that data sets, the unique values there, the unique records were just 20. So the rest were duplicate values. So if I had not actually done due diligence in checking duplicate values, I'll just be building my model on a false data, because it's just like having the replication of the same rows, like 20 to can do the ratio 20 over to 20,000. That's very, very, we just have almost like 1%, less than 1% of the data sets that are unique. So you have to check for your duplicate values to be sure that there are no repetitive columns in your data set. So looking at it like this, you cannot know. But we have the duplicated function. So you can just do, let me load this. The name of our data set is Boston. Boston duplicated, it gives you the false. The whether the column is duplicated or not. So, but for you to actually see the total number of duplicate values, you can just use your sum, because if it's actually true, right, you have 1 as the value, because in computing, false translates to 0, true translates to 1. So in calculating your true and false, right, if you want to calculate addition, if there's a false column row here, it's going to be 1, and then you can easily add up the number. So that's why we're using the false sum function on this, and this tells us that we have 0 duplicate values. So we are good with our checking of duplicates. All right. So the next thing now is to check for null values. Though we know that from this description, the null values are there are no null values, but in a case whereby there are null values, you can use your is null function. So if you do Boston.isNull, this is what you're going to be saying. So it's going to tell you if there are any null functions in each of the columns. So in order to check, for the total sum of null values in each of the columns, you can just do dot sum, and then it gives you whether there is a null value. So if there's a null value in any particular column, it's going to tell you the number of null values. So in a case, assuming you have null values in any of the columns, and the null value is close to, for example, you can have a column where you have 500 null values out of 506 records. So you need to now go back to check what's the column, what's the column all about? Do you really need it? And that's why when you're working with data sets, sometimes you need like domain expert people that have if this in this case, it's more like a general case, or maybe, or when you're working on the in a medical on a medical data set or something that has to do with accounts, you need like an expert, like an accountant, to tell you whether you're not going to be deleting the most important column in your data set. So if now in the case whereby I'm checking it and I'm seeing something like let me just check through the column now. So we have average number of rooms. So rooms are very key, like number of room when it comes to prices of houses, intuitively as maybe as somebody that as an expert in that field, you'll kind of know that, oh, okay, what are the key things that affect prices? Anyway, that's an hypothesis, but then you should know the key things that affect house prices. It could be maybe the number of rooms. If there would, of course, a 1-bedroom apartment, so this will be less expensive compared to like a 5-bedroom in the same location. And then it's not just number of bedrooms now again, the kind of facility inside that 1-bedroom, and so many other things. So if the colon is not so important, and then you are saying that it's 500 and maybe 500 null values, so what you can do is just to drop that colon. But in the case whereby it's a very, very important colon, so you have to do more work. For example, if you're working on a financial data set, and then you have maybe you have to predict the income. You have a data set where you have to predict the income of a particular maybe income of employees within that's an HR data set. Predicts income of employees within an organization, and then you're having columns okay, income is a very key column because that's your column for prediction. So of course, most times for historical data, you might not have missing values for that. But then there could be other key columns. I'm trying to think about columns that could be very important in predicting income. So you could have like the time, the person number of hours the person is going to be spending in that particular job role, the person's job role, some key things that could have impact on the salary of the person. So if you are not having, for example, number of hours, most of the roles, most of the inputs on that particular column as 0, then you have to, figure out what to do with it. So there are different type of imputation strategies that you could use. You could use the nearest neighbor strategy. You could even use clustering. So there are several ways to deal with missing values, right? So you could use people within that. You could check for, that's where your data analytical skills come into place. You could check for related people within that same job role. So if you check, you group, maybe for example, you have so many people's income. I believe we are not talking, we're not using that data set. So but then I'm trying to paint the picture in your mind so that you can just follow along with my explanation. So we are trying to predict income, and we have the number of hours we have like out of like 10,000 records, we have about 9,000 missing. That is a very, very big number. So in a normal case, you could just drop that column if it's not important. So, but if you have to impute, you have to do anything about like making up values for those people that don't have values in that data set. What you could do is you could now analyze the remaining 10,000 people. What is the similarities between those 10,000 and the other 9,000 people that does not have the work hours? So you could use your nearest neighbor strategy. You could use the median score or the median number of hours. You could use the mean, depending on what the result of your analysis is. So missing value is a very critical, you have to do so many data analytical work in order to deal with missing value. But we don't have missing value here. So don't let me complicate things, and let's just move fast so that we can cover all that we need to cover. Okay, so moving forward quickly, the next thing is to do some data exploration. We have satisfied the missing value requirement, duplicate values. Now want to check, let's start analyzing. Let's see the relationship between these features. Are they kind of, what are the relations? Now, because this is a regression problem, there are several algorithms you can use to solve a regression problem. One of them is linear regression. Because of our time, I would have explained the mathematical concepts behind linear regression rather. Okay, so but then we don't have that luxury, so I'm just going to use it in a black box, and I expect you to watch the video because in our past bootcamp I explained the mathematical concept behind it. But then when you're using a linear regression, what it does is that it looks for the line of best fit. So it's good for simple relationship, simple linear relationship. So when you have a data set with a likely, when you have data sets with simple linear relationships, so linear regression is actually a very good model for that problem. Okay, but then when you have complex relationships, I'll be explaining what that means. Let's just move forward so that I can show you with some visuals. Okay, so after checking your information, the next thing is to use your dot describe. So what your dot describe function is doing is showing you the descriptive statistics of the relationship between the features. So we have the crime rate. It's telling you that we have 506 records on that particular column. The mean crime is 3.6. The standard deviation from the mean is 8.6. The minimum value is 0.1. The 25th percentile, that is 25% of the data, that is of the 25% of the data is 0.08. 50, that's the median value. The 50% of the data is 0.25. So you can see, so I'll explain what skewness means now. You can see that this column is slightly skewed. I'll be explaining further. We have then the 75% is 3.6 and the maximum value is 88. You can see that the minimum value is 3.6. The 75% of the data is skewed towards the end of the end of that particular data set. So I'm going to be showing you with visuals. With figures like this, you might not really see the picture, but when we get to the visualization, I'll show you. So you use this descriptive statistics to check for outliers, whether they are out of range values. So if I'm seeing that my maximum value is 88.9, the minimum value is 3.6, and almost 75% of my data set is 3.6, then I believe that there could be an outlier, probably, or probably it could just be a one case scenario. For example, what do I mean by outlier? So crime is talking about per capita crime rates per town. Okay, so we have, for example, you're working with a kind of health related data. Maybe you want to, and inside that data set, you have like pregnancies as part of the colon. And then you're seeing pregnancies, maybe the maximum number of pregnancies, you're seeing like 1 million. That's absurd. You can't have somebody have like 1 million pregnancies. It's not normal. That you know that could be like a maybe imputation error, you know. So that's like an outlier. It's out of range. Pregnancies can even you could have if you're having 500, it's even too much. I don't know if anybody has had like 500 pregnancies. That's a lot, you know. So values. I'm just giving like a picture of what outliers mean. Okay, so and there could be legitimate outliers. For example, you're using an HR data set and then you have salary range, and you're having like most 75% of the people in that company are being paid like maybe 25,000 US dollars and downward. Then you have like somebody paid 150,000 US dollars or maybe 200,000 US dollars. Then it might not be an outlier. Probably the person is the maybe he's the CEO. So when you see out of range values like that, you further investigate who is this person? Why is this person earning 250,000? The people earning 25,000, maybe 75% of people in that department are earning 25,000. So why is someone earning 200,000? 200,000 is an outlier because out of range is not even close to the 75% percentile. So to begin to question that, and because that could affect the results of your machine learning prediction if you don't take care of issues like that. So when you see that you have values like that, so usually you do like some normalization or use some machine learning algorithms to take care of that so that it will not affect your result, or it's a norm. But if it's not an outlier, probably maybe when you further investigate and you saw that the person that is earning 200,000 naira is just a security guard. I mean, $200,000 is a security guard. Then you see that other security guards are earning 20,000. Then you know that this must be an imputation error. Maybe they wanted to impute 20,000 and then the person imputed 200,000. So I believe you can see the explanation. So it's when you do further in-depth analysis, that you get to solve such problem. But if you just, go along with the data and you don't handle such, you might have issues with your predictions. Okay, let's move further quickly. Some persons are not seeing the screen. I'm trying to check on and off. Okay. So moving forward, we have, after doing all the describe and everything, you can now start doing, okay, you can check this. I was just doing further analysis, check the tail, the number of columns. Now we want to check the distribution of our target column. So I just want to explain a bit about skewness, and why do we need to do some further investigation about the target, which is the median value now, because of the prediction of the impact on our prediction. So when you're building your regression models, you have to carefully consider your target variable, because the characteristics of that target variable can impact your model performance. So there are times that you need to perform transformations on your regression model when you have skewness issues. So what do I mean by skewness? So there are skewness is talking about the distribution of your data. So let's just do some visualization. We're going to do a dist plot using SNS, cbon.dist plot, and then we're going to plot it on the target variable, which is MDV. So here you can see that you have a bell-shaped curve, but then it's skewed to the right. This is rightly skewed, and you have the bell-shaped curve here. Normally your target variable should be a normal distribution. That is when your hunch is in the middle. So here you can see that most of your values are close to the origin. Okay, you can see your median value is 20. Your maximum value is around 59 or 59.60. Minimum value is around maybe 5. So here you have like a skewed target. So all of these things you have to be taking note of it. So because that's eventually when you want to improve the performance of your model, you can now come back and start dealing with issues like this if you don't have a very good prediction. So now, if your data is skewed, now you can check skewness because skewness tells you if there is an outlier or not. So because if you're having, for example, you're having a price that is around this region, okay, you see that this one should be so farther away from this the maximum value. So that's telling you that the data is really, is highly skewed. So skewness can actually be positive or negative. So the positive skewness, right, is when your mean is greater than the median and mode. So what do I mean? The median is always around here. Okay, so when you calculate the mean value of this Boston.mdv, and you calculate the median, you can use your distribution stats. Now here, when you check our MDV here, so you can see that here we have our mean. Our mean is what? Our mean is 22. Our median is what? Our median is, that's the 50%. Our median is 21. Of course, you can see the mean is greater than the median. Then from here, we might not, okay, the mode is like the most frequently occurring value. We might not see it here. But if your mean is greater, now here we have established that your mean is greater than your median and is greater than median and the mode. So here you can see that this is rightly skewed, it's possibly skewed, which you've already emphasized. When the tail end is towards the right, that is rightly skewed. When the tail end, that's the tail end is towards the left, is negatively, it's left skewed or negatively skewed. And left skewed skewness is when you have your mean less than the median and mode. For the right skewness, the mean is greater than the median and the mode. And then for your normal distribution, you have the mean equals the median and the mode. That is, everything is on in a bell-shaped form. And so to deal with issues of skewness, you can do some transformation mechanism. You can do a log transform. You can take a log transformation of your target, a square root transformation. You could use quartile transformation, box cut, and so many other transformation on your data set. So you can just keep this handy in case your you want to further improve your model. You might have to do those transformations to help you with a very good result. Another thing you likely do when you're doing regression is also to check for correlation with your target variable. One, you want to check for highly correlated features. If two features are highly correlated, correlation means when your correlation could be also positive or negative. And when two features are highly correlated with each other, it's telling you something that those two features are they are giving the same information. For example, you could have if you're having like age range. Okay, that could be possible. Okay, you have like age range, and then you have like salaries highly correlated with one another. Then it's better to just pick one, or maybe you have them strongly positively correlated. It's just better to drop one value and just use one, because so as to prevent collinearity in your data set. So you don't want to replicate what we are trying, as because what we are doing in machine learning, we are trying as much as possible to select the best features that will be good predictors for our target. Like if you're having 100 columns, can I have, out of that 100 columns, what are my best features? It could just be like 5 features that would actually give me the best prediction for my house prices. It could be just the age of the house, the rooms, the crime rates, and then the tax, and then the other columns that might not really be relevant to it. But then the more irrelevant column you have in your data set, the more the noise in your data set. Okay, so when you're checking for this, you need to check for, that's why we check for correlation. And correlation match is one of the feature selection strategy. There is a library for it. If you are going to be doing it, if you're not going to be doing it manually like this, you have a library, a feature selection library for correlation that helps you automatically select the best features. Okay, so but let's just move forward. So when you do busting.cor, that's how to do your correlation. You see that this, for the crime rates, it does a correlation with all the other, it gives you the correlation of all the other columns. So you can see that crime and crime would normally give you 1, because a column, when you plot it against itself, it will give you like the same. It's a strong relationship. There's a strong relationship between that same column. Okay, so automatically it will give you 1. If you look at the diagonal, you can see that all of the columns against themselves would give you 1. But now you're also interested, what are the other columns that are so highly correlated with crime? So here we can see so many negative correlations. The highest correlation is the tax. So you see that tax, and then it's still, the RAD is about 0.6. But assuming you have maybe like something 0.9 here on this column with crime, then those 2 columns, when you're actually doing your feature selection, you just pick one and drop the other, because there are 2 correlated features in your data set, and you don't want to have that. That is correlation against, between 2 features. Now, we're also interested in the correlation with our target variable. Now, you see, these are MDVs, our target variable, right? We want to see the features that are highly correlated with our target, because we are doing a linear regression, and then we are trying to model a linear relationship, because the goal of linear regression is for a simple linear regression, is to give you the line of best fits. That is, you are trying to model an equation of a straight line. Y is equal to mx plus c, where m is the slope and the c is the intercept. So you're trying to model that line. That is the formula you're trying to get. And the best features that would give you that line are the features that are highly correlated with the targets. Now, the MDV, so we are looking for which features. Now you can see that these are each of the columns against the target. This is MDV. Crime against MDV is giving us minus 0.3. So this is showing us that this might not really be a very good predictor, but you can see 0.36 zone might be a very good predictor. We have a positively correlated value. Okay, so but look at 0.69 room. I didn't see this before as I just figured that number of rooms could be a very good predictor. You can see the correlation, it's 0.69. So this room is a likely very good predictor. Then this L starts, so we have a very strong negative correlation. This could be a very good predictor as well. So when you look at each of them, okay, so you're interested in the ones that are actually strongly positive or close to the middle, and then strongly negative, because those could be like a good predictor of your for your targets. So, but for the first model that you're building, because machine learning building a machine learning model is usually iterative, you have to go over this model development stage over and over again until you get your best model. So most times you don't expend so much energy filtering out all these columns, because you don't even know the ones that would actually be the best model. So there's something called the baseline model. So you could just build your baseline model where you use all your columns as if you don't have so many columns now. In this case, our columns are not so many, we just have 14. We can just use all the columns to build a baseline model. Then that will give us like the worst error rates that we can have with our model. Then we can now start improving from that point onward, because it won't be so good that when after all your work, after you've done all the filtering and everything, you build the first model and it's very poor, and then you now do the baseline model and it's even better than the filter. That's just a waste of time. Like you would have started from the worst, using all of the columns for building your model. Now, in this case, we are not going to filter any column out. I'm not going to drop any column yet. So another way to easily visualize this this table is not very visible. Okay, but to easily visualize it, you can use your heat map from your matplotlib. So there is, sorry, SNS.heatmap. Then you give it the correlation table and you annotate it to true. So when you annotate it, it should give you the values inside. So I'm going to load it. I don't know why these values are not showing. Maybe because I need to increase the fixed size. Let's do 12.9. So it has increased, but then the annotation is not showing. I'll check what the error is. When errors comes like this, you can also check for it out to check the annotation is not working. But then you can see that here, what this is actually saying, the ones that are strongly correlated, this map, it was not it was not correctly. Okay, yeah, it's nice. Okay, this is arranged in order. I thought it was not in the right order. So we have minus 0.6, 2, 1. Okay, so the ones that are negatively correlated, they're in the black color. The ones that are very positively correlated are light colors. So here you can see that these are light colors, and then they are positive, like this here. You can see the positive correlation. So you can just compare the MDV. Okay, we've done that. We compare the MDV with the crime. So you can see for crime, the ones that are actually very, very positively correlated is room. After room, you have zone. After zone, you have black. Moving to, so the darker the color, just like looking at this color scale here, you can see that this is very, very bright, and this is very dark. Then in between, you have the purple in between here. So this L stat is very dark. So this L stat and room are actually very good predictors. And then looking at these ones are in between, the purples are in between, all these ones. This one's to PT ratio 2 would likely be a good predictor because it's close to black. So the white is, the cream is, its MDV is itself. So that's not something to worry about. Okay, now another thing you can do is plot your regression. Use your pair plots to plot your regression plots. So the regression, because we are trying to look for a linear relationship, we would have to, do a pair plot between each of the column names, and the target. So you are setting your data as Boston, SNS.peerplot. So you're supplying it the data, then the X values, that is what I want to have on my X axis. This axis, crime zone. I want like 5 plots on the straight line. So I can use my peer plot to do that. So I have my cream, the zone, the indoors, and all of that. And then against MDV, and the type of plot I want is a regression plot. I set the size and the aspect. So you can see here that this crime is not giving, there's still the relationship. So what we are after, we are looking for a perfect, all the scatter plots as they will be aligned properly on a straight line, everything together, not scattered there. So this, you can see here that there is no relationship here. Here, this is a kind of a negative relationship. This is kind of positive, But let's look at room now, for example. Let's go down. You see room. Yeah, you can see room that is looking correct. You can see that room is giving us that regression line that we want. So it's likely, it's telling us the story, even without you building your machine learning model. You're already seeing from visualization, you're seeing the likely, very good predictors from your data visualization. Okay, so you can see that room. Let's check PT ratio too. Let's see whether PT ratio would give us. I mean, the L stat. You can see the L stat that was very negatively correlated to. The regression line is strong, but in the negative order. Okay, the PT ratio is just in between. The zone is not giving us, so all these other plots, like this is even out of it, And then, so if for regression plots, you're focusing on more of, because most of our columns are actually continuous values. They are not categorical. So your regression plots gives you that opportunity to analyze your column with your target. Okay, so if it's categorical, you could use another kind of plot. It will not give you if it's categorical, you'll not be getting something intuitive. All right, so moving forward now, we've done like enough analysis. Let's start building our model. So here, let's even use, you can see the room and the median value. We can use a limb plot to plot it, and you can see the relationship. It's kind of strong, okay, because of the correlation. Correlation is 0.6 something. Okay. Now let's build our first model, the linear regression model. So like I mentioned yesterday, the first step is to do your train test splits. You split your value. You first of all define your targets. What are the targets you want to use? I mean, what are the features I want to use? You know from your pandas how to select columns, right? If you do Boston.columns, it gives you the name of the columns. You want to select all the columns now. Excuse me. You want to select all the columns, all right? So your you can do Boston, then copy all of these columns instead of typing them one after the other. Or rather, you can just, if you can drop, that's where your understanding of Python comes. You can drop the ones you don't need using your drop function, so that those columns are selected into X. So you have to define your X and Y values. Okay. And after defining your X and Y, your Y is your target. Okay, then you have to split your data set into training and testing sets. Let me see if I can get the whiteboard online. Oh, it didn't tell me to sign up. Okay, so I want to show you quickly what the train test split means. All right, the first step is to import. Now we're going to import train test split from sklearn.model selection. So there are different type of cross validation technique. You can use your train test splits, or you can use your cross validation. But for this class, we'll be using train test splits, and I want to show you what it means on the whiteboard so that you have a background. So because you're building a predictive model, we have our training test. For example, you have your table. It's still loading. Okay. So where's my eraser? Okay. For example, you have a data set, right? Sorry, my lines are not so straight. I'm not using a mouse, but just manage it, please. Okay, so we have X1 as the first as the first feature, X2. I'm not using the mouse, so it's very difficult for me to. You have X3, X4, X5. Those are your targets. That's the 5 features. And then you have your Y as your targets, okay? So what you're doing, then these are your columns. So assuming you have a value 3, 4, 5, 9, 7, 8. I'm just giving a random value. 7, 6. Okay, do I have this is 6. Okay, it's a good number. Oh, this table is too big. It's taking my time. So I have 10, 15, 20. Oh, sorry. I believe you can see my screen. Okay. Okay, let me just keep random values. I would have used Excel or something else, but because I wanted to just show some categorization, let me just use single values so that it won't be difficult to write 1, 2. Why is too difficult to write? Handwriting looks like a toddler's handwriting that is just learning how to write. Oops, I don't know what I was writing here, but let's assume it is what number can I turn it to? Let me turn it to 7. Okay. 6, 1, 1, 1. Okay, so assuming we have this data set, and then we have our columns. These are our feature values. These are our features, and these are our what's our label. So we have to perform, and then we want to perform, want to build a machine learning model, right? And we have this our entire data set. And the goal of machine learning is you're trying to build a mathematical model using one of the algorithms to learn some patterns. You want to use this. These are historical data. This is what has happened in the past. Okay, you're using past data sets. You're building a machine. I mean, you're building a model on past data sets such that when you give it a data set that it has not seen before, would it be able to give me the response of my future values? So in order to do that, I'll have to divide my data set into Usually you do it into three. You have your training sets, your validation sets, and your test sets. But for this class, let's just do our training and test sets. Okay. So divide it. I can decide to split my data set 80-20, 30-40, or anyhow, any percentage rather, so long as I'm splitting it into a reasonable percentage. So I'm going to do like like 4 of my data sets. What did I just do? Okay, assuming I did something well. Okay, so I wanted to say that all of this would be our training sets. Train. This is what we are going to use to train. So we want to keep the remaining 20% to test. Okay. So this will be our what? Our tests. Let's assuming this is a T because of our time. Okay, so we have so we have to divide it into, that's what you're doing in train test split. So you're dividing this towards your train and test, so that you're going to build your machine learning model on training data. And after it has supplied, because when you're building your machine learning model, right, it's going to give you this is your entire Y. So you now have like, this is your Y original Y, then you now have your predicted Y value. That is what the model would eventually predict for you eventually your after you finish building the model. So now your training sets would be what? X train and Y train. That's the first you are going to have 4 values. That is, you are going to have like X train. This is your entire X train set, right? From X1 to X5 is your X train set. Then this is where it stops. Then you have from Y to this point, this is your Y train. Then you have your X test, this place, this entire region. This entire region is your, oh, this is a very big, this is your X test, and this is your what? Your Y test. This is your, the other part is your X train and Y train. Let me just separate it with the red. So this is your X train, this is your Y train, this is your X test and your Y test. So what you're doing is that mathematical function is going to be applied on your X train and Y train, such that as is creating a mathematical relationship. For example, you're doing your equation, you're doing a linear regression. So it's learning that, okay, for every X1, X2, X3, X4, X5, the result is this, okay? For all of this, based on the mathematical function, the result is this. For all this, the result. So with that, it's going to create a formula. If it's your linear regression formula, which says y equals what? Mx plus c. So here you have your y, that for every value of y, there is an mx plus c. So this is the equation of the straight line that you're going to use to make predictions. So now, after creating this model, right, you're not going to use your test set to evaluate the result. Already you know that the result of this test set is going to give you a 4, and this other one will give you a 1. So you're going to now use this test. This is your X test, and you're going to use it with your equation. That is, you're going to give it, for example, this equation will be what? Mx1, I can't write so much here, plus mx2 plus mx2. I'm not using my mouse, so it's very difficult. 2 dot 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 mxn. But I believe you can see plus c. So this will be what your equation. So you'd already know the value of your x1, right? You know the value of m and you know the value of c from this equation that has been generated. So you're not going to use that equation to calculate your new y. So your new y will give you a particular value. Probably if your new y is giving you a 4 and this one is giving you a 0, then you now have to calculate the error. That means there will be an error. So the closer the error is to 1, the better your model. So eventually, if we are working towards the best model where we have our model give us the correct predictions, okay? Where you have for every of your new for your test set, it's giving you what is supposed to be, because so that you know that if you're having to evaluate it on a test set and it's working like that, then for future values, okay, for any other new value I'm going to use, I'll just need to use this formula and then it supplies the answer. So that's what prediction does. All right, so you're using there's a mathematical function, an underlying formula. So when you hear of the random forest uses the decision tree formula, we have the support vector machines, you have the linear regression, you have the KNN, and so many algorithm, XGBoost. They all have their mathematical functions and they have the peculiarities. So most times when you want to do research, you have to study the underlying mathematical functions. Why are they? What kind of data set are they used for, and all of that. Okay, let's quickly run because of our time. Okay. We are going to look at go back to our Boston now. So I want to explain. I was just trying to explain what was going on here so that you have a background of what we're. So what we are going to do now is all the explanations I just explained to you. This is just the line of code. So we have our train test split function already written for us. So you can just import it. Then you have your X train. That's the X train I talked about. X test, Y train, and Y test. Then you use the train test split function, and it takes, if you do your shift tab, you see all the arguments it takes. It takes your test size, your train size, your random state, and whether you want it to be stratified. You want a strata. All right. So your X value, you supply it to your future and your targets. And then the test size, this is where you supply the percentage. So here we are using 70% for our test set and 30% for our train sets. So we're saying our test size should be 0.3, and then your random state could be any random value. All right. So if we want to print the shape of this our X train, you can see that our X train dot shape is now what's 3. The total record is 506. So you can see that your X train, that is, in our previous example, we had like 4 rows as our X train. So here 354 is our X train and 152 is our X test. So if you want to print it to see what it looks like, so let me just run it so that. Oh, okay. So I think I loaded it correctly. So you can see, sorry, it's a function. Let me just do it correctly. So you can see that it's still a data set, right? What your X train is just giving you now, it's just 354 of this. You can see that your target variable is not there anymore, right? So it's just this part that is there. The Y is not there. All right. So that's what is in your X train. The X test, if you check your Y train, let's check our Y train. You see that it's just only the single Y that is there. You can see that all just the target values that are there. Okay, so moving forward, after doing your train test, now is the time to build your model. So all the story of the mathematical function and everything, this is where it's happening. So here, to build your model, you have most models, they have their library. So for linear regression, it's in the sklearn.linear model library package rather. So we have from sklearn.linear model import linear regression. So this is the step. After importation, instantiate. You instantiate, what you're doing is this same linear regression, you create, you give it a new variable right? You are saving. This is the linear regression, the y equals mx plus c function that you want to use to train your data. This linear regression is been written for you, right? You just want to apply it on your data set. And this is the process of training. This is the fitting process. So here, you're going to define, you are saving that linear regression model into a variable name that you can use for your fitting. Okay, so the next step is using this linear regression. You call your dot fit method. So what you're doing is you're fitting. Now we are fitting the x train and the y train. Remember, where is our x train? This is our x train, right? Our x train, and then this is our y train. This entire part is our x train and y train. That is, we are learning a particular mathematical formula, x train and y train. Okay, so that's why we're using x train and y train. And then after creating that function, now we have our model already built. It's now time to predict. We make prediction on the x test. So here after getting our function, this is assuming this is our new linear regression model that had been learned. You're going to use the x test. This is the x test. You're going to use it to make prediction, use to do your predicted y. So that's what we are doing here. Linear regression, that's the name of the model. The formula dot predict, you call the predict function on your x test. So you're storing it into your y pred. Now your y pred is the predicted y. So you don't have to calculate the error, just like what you were trying to calculate. To calculate the error between, error is just what your prediction minus your true value. Okay, so usually there are different type of evaluation metrics for linear regression. We have the mean absolute error, we have the root mean squared error, we have the mean squared error, we have the R squared, we have different one, but the most frequently used, you usually use the root mean squared error, or you could use the R squared as well, or you could check the score of your data set, I mean, of your the performance. So you use the metric as for mescaline important metrics. So for your mean absolute error, I might not be able to go through the formulas because of our time. Our time is fast spent. So I'll leave you to watch the previous videos for the last bootcamp. It's under the playlist Data Science Bootcamp on our YouTube channel. So you can check that for the explanation of the mean squared and all of that, and the mean absolute error. So when you apply your metrics to mean absolute error, you're supplying the test set and the predicted y. You're checking the error rate. So you're using the three different errors. And here you see that the mean absolute error is giving you a 3, 19, and 4. So if you look through the explanation of what each of this error means, you understand what the figure represents. So, but then the goal is to reduce them as much as possible to a 0. Okay, so the lower your error, the better your results. All right, so here we are getting a very minimal error, but if you calculate your score, let's calculate our our log score, our accuracy, just like an accuracy score. Okay, you can just do your scoring model to check what the score of this model is. Lane reg. Now you can see that it's 78%, which is very low. So it should be close to 100%. So there are several things that could be done to improve the performance. The first thing I did here was, okay, now here, before increasing performance, I want to just show you what the formula is now. So if you use your intercepts, you can print your intercept. This is your intercept, linreg.intercept 46, your coefficient. So these are the x1 coefficient, x1, x2, x3. So if you're going to map the coefficients with the with each of the columns, so you can see the coefficient for crime is minus 0.09 and all of that. You can see each of the coefficients, right? And then if you do your performance, you want to check your predicted value with your test value. you could just do a scatter plot, and then you see that you're actually focusing on a very straight line, kind of relationship, because if your predicted and the y value are actually on that they are close to zero, you'll be having like a perfect straight line. Okay, so you can use the scatter plot to plot. Then you can also use your dist plots to plot the area on that curve of your residuals. That is plotting the residual values. You want to check what the residual value of your that is the difference between the predicted value and the and your test values. Okay, so I was trying to use another algorithm. There are several things I can do to this. You can start doing your feature selection, reduce the number of features, and so many other things. But then there's a very good algorithm that works well with linear models as well. It's called the random forest regressor. So it's still the same process. You do your sklearn.ensemble, import random forest regressor, instantiates RF equals random forest regressor. You fit the same process. It's just what is just changing is just the algorithm. You fit it using rf.fit, then you make your prediction. So when you do this, let's see what our result looks like. You can see that our root mean squared error is now 3. It jumped from a 4 to a 3. Our MSC is the most interesting one. It jumped from 19 to 9. That is very, very, a big super mega improvement. So let's check the accuracy. You see that the accuracy at even, okay, maybe because I'd already loaded something else. Accuracy is 89% from 78. That's a big improvement. So let's check, let's print out that our scatter plot now. You can see that it's going to affect your scatter plot. Scatter plot is looking more perfectly on a straight line compared to the other one that you have. Okay, and if you see your residuals as well, you see your residual is almost like a bell-shaped curve. It's almost so normal. Okay, so here, so eventually, finally, if you get your perfect model, you can now export the model as a pico and implement it in production. It at the production level, all right, so that you can test it um with other data sets, and people can use this model. But that's not all to it. There are so many things. Each of your data sets, they come with their unique challenges. Okay, so you have to understand what, and then it comes with practice. The more you practice, the better you get at building your ML model. So I'm going to stop here for now and take questions. Do you have any questions so far? Any questions? That means you understand everything. Any questions? Okay, Adela is saying something. All right. Okay, you need to go over it. All right. Okay. All right then. You can take some time, go over it. The recordings will be available on the YouTube. We'll upload it on YouTube. You can subscribe to get the notification. Then it will also be on the LMS. We link it up on the LMS as well. Yeah, so that you can go over it and try it out. And then if the more you work on more diverse kind of problems, you see that you get better understanding of the whole process of the building the machine learning models. Okay. All right then. thank you all so much for today's session. I believe you learned one or two things. Machine learning is actually very interesting. Yes, several this okay, I didn't even go over this. Re-engineering the features because of our time. I could not do that. So because I have a better model on this, I can now go ahead to re-engineer features using all of the maybe feature selection process algorithm, select some best features, then apply it on the one that gave me 89. I can increase that accuracy to actually close to 100. But then you have to be sure of there's something called overfitting and underfitting. You have to be sure that your model is not overfitting, that he's learning the over learning all the patterns on your data, and then it so fits your training set that when it gets to the test sets, it underperforms. That is, he has mastered so much, like it's so fitted to your training set, and then it gets your test sets to underperform. So you have to watch out for that as well when you're building your model, because you might be thinking that, oh, I'm getting 100% on my training data, but then when you now evaluate on your test data, you're getting a very low accuracy score. And that's why you divide your data set into how you test for that. You divide it into more than two piece two here we're dividing it into just training and test. So you have like that's where you use cross validation. You can divide it into 5 so that you can test across different batches to be sure that your model is not overfitting. All right, so that's another level. Let's stick to this for now so that I don't confuse you with other concepts, but just go through this, and then if you have any question, you can drop it on the group, and then we'll meet again in the next class. So till we meet again, enjoy the rest of your day, and thank you for joining. Okay, bye for now. Oh, all right. I'm just saying, how do you choose a suitable percentage to split and random? So the percentage is up to you, it doesn't affect your model accuracy. Then the random state is just is just for randomizing your data set. So it's not it's like you building, it's just like a seed function just when you do your random number. So it also does not really affect your accuracy score. So we have some other hyperparameters. Those are not major hyperparameters. We have some other hyperparameters that you can tweak inside your linear regression model. Let me check if I can show you some here under random forest. So inside here, we just used all the defaults in random forest. So if you check, yeah, other things, the default is number of estimators. So if you read the documentation for random forest, it will tell you what each of these parameters mean. So you can change the value. So if you want to further improve the performance of your model, you can decide to change the number of estimators. You can change the criterion of your evaluation. You can set the maximum number of features based on what the kind of data set you're working on. So those are the things that can actually affect the value of your predictions. Okay, those are hyperparameters that you can tune within your algorithm that can further affect the values of your prediction. But for the splitting is just normal splitting. 80 I can decide to use 70-30 depending on you can decide to use 80-20, but the most important thing is that you're using the bundle of your data set to train. Depending on the size of your data set, if you have the very large data set, you can decide to even divide it into 50 50, 25, 25, and then you have plenty data set, but you need a very good number of data sets to train your machine learning algorithm. All right. I hope answered your question. Okay, then if there are no other questions, do well to enjoy your weekend. Use the weekend for catch-ups, and then if there are any questions, you can just ask and then would respond to you. Have a nice day, everyone.